Okay, hello, welcome YouTube to this video of me exploring SpiceSharp. Okay, here's the project I kind of wanna deal with. Okay, so my end goal in mind is to have a solver that sort of is able to solve fluid flow. All right, that's a lot of things on my channel has to do with fluid mechanics. So let's say you have a centrifugal pump here, okay, and some pipe systems. And this centrifugal pump, it will pump fluid into a pipe that actually like so-called splits in two. Okay, and then you have some sort of components in each of these, let's say a heater, heat exchanger, etc., etc. Okay, and how do you solve this system of equations, right? How do you solve this system of equations? Okay, you have some volumetric flow rate here. We have a volumetric flow rate in like some meter cube per second, or okay, you need to consider volumetric flow rate across these branches, and then you kind of need to find out, oh, okay, each of these branch has a different resistance to flow, therefore the volumetric flow rate will differ in between each of these, and this pump will have a certain increase in delta P, or change in pressure, and of course as you flow along the pipes and each of the components, the fluid will decrease in pressure. Now thing is, I want to solve these fluid flow equations very quickly, and then after that have some other algorithm that solves for heat transfer as well. Of course you can use DWSim to solve these kind of very simple setups, but I need it to solve I need the fluid flow equations to solve very quickly, whereas DWSim or HYSYS, they solve from node to node. So let's say you have a material stream here, or fluid flow stream, okay, that goes into a pump. Okay, it goes into a pump. Ooh, my bad, sorry. Okay, it goes into a pump. Okay, a pump, a fluid flow stream that flows into a pump. You need to actually solve all the thermodynamic properties of this fluid flow stream first, and then you solve the fluid flow equations within the pump. That's how DWSim algorithm usually works. And the thing is, this may not be fast enough for what I want. I want a real-time simulation, dynamic simulation of fluid flow schemes and setups, all these kind of things. So I need this fluid flow equations to sort of solve instantaneously or near instantaneously, but I do not really need all the chemical equations there, and I will probably add the heat transfer equations to solve later, and I'll probably solve them in parallel with these fluid flow equations. Okay, so they're kind of loosely coupled, but yeah, that's the deal of the thing. Okay, that's the deal. So that I can have the whole thing running in real time, because speed is of the essence, calculation time is of the essence. So you do not want to burden the solver too much. Okay, what's a good tool to learn to solve this thing? Okay, where can we have a template from which to start programming? Okay, after, let's say, just take for example that all the fluid flow properties like nu and rho, this is a kinematic viscosity, usually in meter square per second. Okay, this is in meter cube, okay, or kg per meter cube, kg per meter cube. Okay, all these things, let's say you have the temperature dependent properties of this, you kind of use some external program to supply this. Okay, so after that, what do you do, right? What do you do with this? Okay, you have this, let's say you have this node and this node. What can you do, and what kind of program can you use to template this off? So this is where SpiceSharp comes in. Okay, SpiceSharp actually is a circuit simulator. Okay, so that's the idea I'm looking at now, I am exploring. So within circuits you have some kind of a battery, all right, and then you go through, this battery flows through a resistor, okay, and resistors kind of have this node node and network kind of a model. Okay, so you use Kirchhoff's current law to sort of solve for these solve for the voltages across each resistor. Let's say you have R1, R2, R3, and a voltage source, maybe what, 1.5 volts, 1.5 volts. Then each of these will have some kind of fixed resistance. Okay, so this is usually the setup of a circuit. Okay, of a circuit kind of a setup. And what kind of happens here? You can actually make this analogy that voltage kind of you can think of it as a kind of a pressure drop or pressure change, that kind of thing. It is analogous to that. Of course, you can also put the hydrostatic pressure down there, H rho g. This is the pressure due to the height, and then of course there's a pressure drop there. Okay, so both contributions to pressure, whether it's hydrostatic pressure or this, can actually be sort of analogous to voltage, whereas the current in the circuit can sort of be analogous to the volumetric flow rate. Okay, like what, meter cube per second, or maybe even mass flow rate if you want to have it that way. But usually the thing is, it is nice to have it in volumetric flow rate. Why? Because when you talk about power in a circuit, usually it's calculated like so. The power in a circuit equals to the current times voltage, whereas when you talk about the power, the energy flow rate, it is actually the volumetric flow rate times delta P. Okay, you'll see that the units kind of work out. Sort of, yeah. Because PV equals to a work unit. Okay. So if you think of work done in a gas, usually we integrate PdV. Okay, this is a thermodynamics thing. Work done equals to PdV. Okay, so PV is a unit of work, and then this thing is volumetric flow rate, so it's a volume per second. So both of these, when you put them together, they will also result in the same power units being here. So that's why it is nice to have delta P kind of analogous to voltage, and volumetric flow rate kind of analogous to current. So what current is what? Current is this is actually what? How much charge per second? Okay, how many charge per second, which I use Q, charge per second. All right. So whereas volumetric flow rate is also, well, sometimes people use volumetric flow rate as Q, but I'll put volume per second. This is a volumetric flow rate per second, and then you can think of voltage, right? This is voltage. This is equals to how much work is done per unit charge. Okay, voltage is work done per unit charge. Okay, joules per coulomb is volt. That's the units. Whereas pressure drop, now you can think of it like that. It's actually work done per unit volume. Okay, work done per unit volume. Okay, so remember that work done equals to PV, or integrate PdV or whatever. Okay, so you can see units wise, this actually works out very nicely. Pressure can be thought of as a work done per unit volume. So in a sense, the units for this actually work out very nicely. Is everywhere you see this charge, you just replace it with a volume unit, and all the units will kind of settle themselves pretty nicely. Okay, so this is why electrical circuits are sort of nice a good analogy for it for electrical circuits is usually fluid flow. And if you want to use a electrical circuit solver, you can potentially adapt it to solve fluid flow. Now this is where the analogy breaks down. Most resistors actually obey Ohm's law. So Ohm's law states that, I'll just put a capital omega down there, which is usually the symbol for ohms. Okay, so what happens in Ohm's law? Okay, a resistor that obeys Ohm's law will have a constant resistance. Okay, that means resistance equals to voltage over current. Okay, and this is the resistance is sort of constant. You don't really change the resistance to current well, no matter what the voltage is. Okay, if the voltage is 5 volts and the resistance is 2 ohms, then the current will always be 2.5, for example. If you increase the voltage to 10 volts, right? If you increase the voltage to 10 volts, then and your resistance is still 2 ohms, then you will get 5 amperes. Okay. However, for fluid flow, okay, flow resistance will not work out like that. Flow resistance will not work out like that. Why? Okay, because well, if you try to take this analogy all the way through, yeah, you will notice that. Okay, you will notice that if this you have this equation set up, delta P over what? Delta P is analogous to voltage, and I is the volumetric flow rate. So let me just put V down here, or maybe I will just use Q, because you might get it's easy to confuse if the symbols are all the same, right? V for volumetric flow rate and V for voltage. Okay, can get very easily confused. Okay, so what is this pressure drop? Okay, the volumetric flow rate will be whatever the volumetric flow rate is. Okay, but pressure drop in terms of volumetric flow rate, what is it? Okay, usually there will be some sort of friction factor or CD down here, or coefficient of drag. Okay, coefficient of drag. Then you'll have half rho u square. Right, this is the dynamic pressure. Okay, this is the dynamic pressure. Okay, so yeah, half rho u square is usually okay. Fine, that's kind of a flow rate sort of a thing. Half rho u square. Oh yeah, that's dynamic pressure, not flow rate. Yeah. Okay, so if you have, say, Q, and then you want to relate it to the what do you call that? You want to relate it to this U over here. You notice that yeah, if you have average fluid velocity times A, and that will equal to Q. So this half rho u square is actually like a Q square kind of a term. If you want to change it around, you'll notice that this is actually proportional to Q square. Okay, this is actually proportional to Q square. Okay, so what am I saying here? What I'm saying here is that Ohm's law does not work very well for fluids, because the pipes and all that do not behave like resistors. They do not obey Ohm's law. Okay, first thing first, from this equation you can already see there's a Q square term up here, because U square is kind of proportional to Q square. The only thing that is there is a cross-sectional area. Okay, cross-sectional area, that is your constant. Okay, of course the other thing that you have to pay attention to is CD. CD is some coefficient of drag or some friction factor. Okay, I think coefficient of drag isn't quite the right term to use here, but this thing is some non-linear function of a Reynolds number. It is some non-linear function of a Reynolds number, and Reynolds number is, I guess, in a sense, sort of proportional to Q, but not quite. Yeah, not quite proportional to Q, because there's a U times X right over there. Okay, so it's sort of proportional to Q, but not quite. But this function here, for the most part, is kind of non-linear. Okay, so there is some sort of non-linearity within flow resistance right here. So why don't solvers use the same algorithm? It's because of this problem. Now, thankfully for us here in SpiceSharp, there is this acknowledgement that let's see. There is this acknowledgement that most of the time you will not find let me use the right page. Okay. Yeah. Most of the time you will not find that you will find electronic components. Okay, see over here under modified nodal analysis in SpiceSharp. Yeah, you'll see them use Kirchhoff's current law, which is basically conservation of charge. Okay, it's like mass balance in chemical engineering, except here we use charge balance, right? Alright, so thankfully here it says what? Electronics world is littered with non-linear components. Non-linear components are what? Non-linear components, what do they mean? It means that, you know, the resistance is proportional to Q square or Q to some non-linear function. It doesn't fall neatly within this Ohm's law. Now that's of course putting it very simply, or oversimplifying a lot of things, but essentially that's, in this context, that's what we need to know. Okay, the flow resistance for pipes is non-linear, but also in the electronics world, a lot of things are also non-linear. Okay, so it says here what? The resistor is a linear component because current and voltage are connected via Ohm's law, V equals IR. However, a diode here is a non-linear component because the diode current depends on the diode voltage upon the following equation. There's some exponential thing down here. Okay, so in order to solve a circuit with non-linear components, we have to resort to iterative algorithms. Okay, SPICE-based simulators almost exclusively use the Newton-Raphson algorithm. So what's this thing here saying? It says here that this circuit solver, it actually solves for non-linear components. Okay, we just need to construct the matrix using this Newton-Raphson method, and yeah, basically that will help us to get closer to where we want to be, right? So yeah, so next time, I guess the subject for next time will be to start talking about these things. Yeah, why do I have this here? Okay, but never mind. Yes, next time we'll be wanting to talk about matrices and all that. So yes, I want to go through what this Newton-Raphson algorithm, how does it work, and then hopefully okay, my goal for this project is to explore SpiceSharp to an extent that I can use these Newton-Raphson solvers to solve for fluid flow equations eventually. Okay, so because as we see from the get-go, all of these are non-linear, so we don't have to use Newton-Raphson method. We have to have some good understanding of what Newton-Raphson method is. Okay, so I'll stop for now. I'll see you probably record more next time. Bye.